This is Yamamoto. Hello. So I want to thank the Q2B organizers for this wonderful opportunity. So from my perspective as a researcher, I'd like to talk about InQuanto, the software. So I'm Kentaro Yamamoto. So I have been a researcher based in Quantinuum's Tokyo office since 2020. So I'm the first researcher to be based outside the UK or the US. My background is in quantum chemistry. Based on that experience, I've been working with the Cambridge main development team and doing R&D in Tokyo. For example, on the software development side, InQuanto Pi SCF is a software product. I'm the main author of that. For algorithm development, I've been involved in the development of noise mitigation technology. So, based on that background, I will introduce InQuanto, a quantum chemistry software that I've been involved in developing. Through this talk, I hope to give you an idea of what is InQuanto's approach, or what is InQuanto and what is Quantinuum's approach to quantum computational chemistry. So this is today's agenda: general overview, company overview, positioning of InQuanto, and I have a small demo as well. So let me give you the general overview. So first, a brief introduction to Quantinuum. Quantinuum was formed in 2021 through the merger of Cambridge Quantum and Honeywell Quantum Solutions. We have more than 350 researchers globally, including the Tokyo office. We're a very research-oriented company. Quantinuum is one of the few quantum computer companies that can provide a full stack of hardware and software. So I'd like to show you the product of Quantinuum. So on the bottom layers, that's closer to the hardware. The upper layer are closer to the application. So one product I want to explain is Quantinuum hardware H series. So this H series is an ion trap device that boasts the world's highest quantum volume, developed by Quantinuum. There are lots to talk about in this area of hardware, but I'm here today to talk about InQuanto, so I'm going to skip right over to that. So next is Ticket here. Ticket does not rely on back-end or hardware simulator. It allows seamless development. It's a quantum software development kit. And InQuanto is what I'm going to focus on today. That's built on Ticket. And what it assumes is that, it's designed to connect computational chemists with quantum computers to provide them seamless access. That is the aim of this development. So in concluding this general overview, I'd like to talk about why Quantinuum is developing InQuanto. The development of InQuanto originally started as a tool to support collaborative research between our company and our partners and academia. And several research results using InQuanto have already been published. So if you are interested, please also listen to the presentation by Hira Iwa, member of our company. She'll be speaking tomorrow morning. From here, I'm going to give you an overview of InQuanto. And here I will explain from my technical point of view what you can do using InQuanto. So what kind of computer, regardless of the type of computer used, why study computational chemistry in the first place? Well, there are various motivations. Now, I mean, there's nothing better than being able to actually conduct physical-chemical experiments, but that can be quite expensive. If you can obtain results of an experiment with high accuracy by calculation without conducting the actual experiments, you'll be able to reduce huge amounts of cost and time necessary for that experiment. The basic theoretical framework that makes this possible was completed more than 95 years ago, and so at least in principle, it can be applied to the determination of various chemical properties such as ground state energies, spectra, reactivity, and reactions. So you should be able to calculate these things in principle. Now, even in this modern age of developed computers, it's actually very difficult to rigorously apply such a framework to practical systems. That is known. On this point, I think you'll be hearing from various perspectives here. And it's a quite simple explanation for chemistry. The main reason is that the computational resources required to adapt rigorous computational methods increase exponentially with the size of the system. So the size of the input increases exponentially. So it's not realistic. And so it's unlikely that the computational resources of classical computers will grow exponentially going forward. So it's necessary to consider a radically different approach. And Quantinuum believes, and I think you do too, that the quantum computers are the most promising solution. Now, devices of today. In order to use them for industrial application, I mean, the motivation is easy to understand, but there are some issues. And in order to use quantum computer application in chemistry, you need to overcome those issues. For example, a workflow issue. So this you need to combine various different types of layers to build the backflow. And to have a scalable backflow is or workflow is very difficult. And there's a scalability issue. So you will not be able to calculate large molecules if you apply small systems. And of course, there's the noise issue, especially in the near term. The noise will limit the accuracy. I think that situation will continue. So the issue of noise has to be resolved some way. And then there's the back-end difference. So the quantum hardware, that is, that's advancing day by day. And to develop programs for each is a difficult task for application. So on the application side, you don't want to spend time on that. And so there are those issues, and you have to be able to provide solutions. And so InQuanto is designed to provide such solutions, and I explained the workflow of InQuanto here. So I won't go into the details. It's a collection of modules, InQuanto is. And the closest to the user is the input. So the nucleus coordinates and the basis function information, these kinds of computational chemistry input is provided. And then that information is passed to mapping. The computational chemical information is converted into a quantum computational information. In this step, the usual chemical calculations are performed as a pre-processing step, and information is passed to method. Then the chosen algorithm is used to construct the input for the actual computation by the quantum computer. And then Ticket then executes the computation on the hardware or simulator, and finally returns the output in a form understood by computational chemists. That's the basic workflow. The user has access to all of the modules. It's designed so that there's easy access, so you can use it as is, or you can choose one and incorporate it into your research workflow and test various new ideas freely. InQuanto has many algorithms implemented, and I can't go into detail of all. So I'd like to take one example, VQE, to explain unique features of InQuanto. VQE, or Variational Quantum Eigensolver, I think you know, is a quantum classical hybrid method. The basic concept is to let the quantum computer do what it is good at and let the classical computer continue to handle the rest. Now, in the context of quantum chemistry, there is this energy expectation value, and you want to optimize that. And the status of electron is mapped to the parametrized quantum circuit, and the energy expectation value will be estimated by the quantum computer, and then it will be optimized for these parameters. So this kind of calculation, if you implement it in a simulator with no errors, it's relatively easy. But in actual hardware, if you have to code to actual hardware, this becomes a rather difficult task. What kind of difficulties are there, and how does InQuanto try to solve this, is what I would like to explain in the InQuanto demo. So I said that it's an example of calculating expectation values. The key to getting meaningful results from NISQ devices, well, there are two major things. One is to generate as shallow a circuit as possible and to reduce the effects of noise. So error mitigation technology. So InQuanto offers solutions for both of these factors. So for shallow circuits, chemistry-based optimization techniques are provided, and also the ticket. The quantum compiler also has that optimization, so combine both for the optimization. And InQuanto also has easy-to-use noise reduction techniques. And you can optimize the performance of the hardware that you can use. For the sake of clarity, let us consider our simulator, not the hardware, with these parameters. C0 error rate 1%, read out error rate 1%. So let's assume those are the error rates. And so this is chemistry. So let's look at the hydrogen molecule, a very easy example. And we use UCCD, unitary coupled cluster doubles ansatz, what's used often in chemistry, and do a demo. So this is a variational algorithm. So we optimize the parameter, but we're doing expectation value calculation. So optimal parameter is already prepared, and we compare that to the exact calculation. So for comparison, let's first look at the result of applying the algorithm naively. So if we naively construct the UCCD ansatz using InQuanto, the circuit depth, C0 depth, is 48. And I want you to focus on this. If you naively apply this and calculate, you have minus 50 point something. That's the energy result. Compare that, you have 1,000. So there's a huge overestimation. So even with 1% error rate for a chemistry calculation, if you apply it naively, you get a meaningless result. As a chemist, you're very disappointed with this, but what happens when you use InQuanto? So in terms of making the circuit shallower, so in addition to the usual circuit optimization by ticket, InQuanto has chemistry-aware circuit reduction. So there is the symmetry that has the molecule that the molecules have. So you apply that, and you can reduce the circuit depth quite substantially. Even with the default, there is optimization, but by designating the point group, then you can make the circuits shallower. So this is the only thing the user specifies, and then you can leave it to the system. And you apply this, and you had 48 C0 depths, now has reduced to 3. Nothing to be done by the user, just press the button and you can reduce the circuit depth by this much. So let's talk about the noise mitigation. In InQuanto, there are several noise mitigation techniques. So partition measurement symmetry verification, PMSV, a technique that I was engaged in development, is used here. So what the user does in applying PMSV, so this uses symmetry in a clever way. So you calculate this symmetry beforehand, and you give that, and then you have this apply. So you just specify that, and then you can use this noise mitigation technique. The result, if you apply this, well, earlier you had the 1000 some kilojoule per mole. There was a huge overestimation. This time, with this application, you have minus 25.7. So even with 1% error rate, it's still high, but quite close to and comparable to the exact calculation result. So that energy could be calculated more accurately. With better performance of hardware, you can apply it to even more complex molecules. So the message I want to convey to you is that there are various error mitigation techniques, and so for hydrogen molecule is understood better, but in aiming for quantum advantage, you need steady effort close to the hardware. That's what we feel. And the demo that we conducted shows how we're close to the hardware. We're making this steady effort. It's sort of a philosophy that we have to be close to the hardware. So we like to continue to collaborate with hardware to enhance the hardware itself and also to optimize that hardware. We're going to focus on those dual objectives in our research. So I'd like to conclude. The biggest point I want to convey to you is InQuanto is a quantum chemistry platform that you can use today. So as I said, there are researchers at various levels, and some people in close to application, some people doing calculation in supercomputers, and regardless of the level of research, you can immediately use InQuanto. That's what we mean when you say that InQuanto is a platform for today. And latest quantum algorithm and circuit optimization tools are implemented here. And thanks to Ticket, H series and third parties back end can be chosen. So you can use it for the hardware that you have. And you can mix and match high and low level modules for optimum results. I think this is also important. Researchers like me, we want to work at the very detailed level. InQuanto allows you to do that. So that concludes my presentation. Thank you very much.